I thank you, learners. This is Mr. Odingo, and I want to welcome you to the lesson of today. And as you can see on the board, we are going to look at the topic called bonding and structure. And this chapter here, we have up to 3 sub-chapters in it. One of them will be looking at ionic bonding, ionic bonds. We have covalent bonds. Then we have metallic bonds. This is what we are going to look at, and today we are going to start by looking at what we call ionic bonds. And many times we have to first of all start by understanding what ionic bonds are. So when you look at ionic bonds, the first thing we have to look at is why do bonds form? Why do bonds form? If you understand why bonds form, then we are going to actually understand how this bonding takes place. Ionic bonds, or any other bond for that matter, form because the atoms are not stable. Atoms are not stable. So when atoms are not stable, they have to try to be stable. And as we know, they may try to be stable by either gaining electrons or losing electrons into their outer energy shell or out of their outer energy shell. Let us try to look at the atom of sodium. We know sodium is number 11 in the periodic table, and therefore the electronic configuration of sodium is 2, 8, 1. In this case here, sodium has 1 electron in its outer energy shell. Let me just sketch its atomic structure. If I sketch its atomic structure, this will be sodium with 3 energy shells. The first energy shell will be having 2 electrons. The second energy shell will be having 8 electrons. And the last energy shell will be having 1. You realize that I am grouping these electrons in 2, 2. That means that, as we have studied before in electronic configuration of atomic structures, an orbital must have, we have orbitals having 2 electrons each. That is why we can say this is one orbital, this is another orbital, this is another orbital, this is another orbital here. Okay, now this atom here is not stable, because we know for an atom to be stable in this energy shell here, and sodium being elements in the first 20 elements, this must be having 8 electrons out here, but it is 1. So sodium will be stable by losing this 1 electron in the outermost energy shell, so that after losing this electron, its outer energy shell will also be lost. So we are going to have the outer energy shell of the sodium ion being the one with the outer energy shells. If we have chlorine, chlorine is number 17, which electron arrangement is 2, 8, 7. Chlorine here has 3 energy shells as well. And these 3 energy shells, the first has 2 electrons, the second has 8 electrons, and the outermost energy shell has 7. If I draw that and I want to compare these 2 atoms, this one is sodium atom, and I've said that it has 1 electron in the outermost energy shell and it is not stable. This one has 7 electrons in the outermost energy shell. It is not stable because for it to be stable it needs to have 8, and therefore it means that chlorine atom will need to gain 1 electron in its energy shell. Sodium atom, on the other hand, will have to lose this 1 electron. Now, the kind of a very important arrangement here. While sodium is going to get rid of this 1 electron, chlorine will have to take that electron so that its outer energy shell is filled up. And that is what's going to take place. There's going to be a transfer of 1 electron from the outer energy shell of sodium to the outer energy shell of chlorine. Once that happened, remember that the movement of electrons is occurring because both the atoms are not stable. sodium needs to be stable by losing 1 electron, chlorine needs to be stable by gaining 1 electron. Once that gaining or losing takes place, these atoms quickly change into their respective ions. For example, sodium, therefore, after losing 1 electron, it will change into sodium ion. Sodium ion in this case will not be having the outer energy shell, because once the electron is lost, that energy shell also is lost. Now we know that an ion of sodium or any ion must be bracketed, so we are going to have here +1. This +1 means that we have lost 1 electron, and so that the number of protons in the nucleus here, which are positively charged, are more than the number of electrons in the outer energy shell by 1, and that's why there's an excess of 1 proton. That's why we have +1 here. But when we come to chlorine, we said chlorine is gaining 1 electron, and that electron is being gained from sodium. So we are going to have chlorine here, or chloride ion. This is the first energy shell, the second energy shell, the third energy shell. It has also to be bracketed because it is an ion. And in this case here, we have to notice that I made a mistake by drawing the crosses on for both atoms. But in this case, I want to correct that one by ensuring that if this one we are using crosses, then chlorine atom you have to use dots. So I will be using dots here to indicate that these atoms are actually different atoms, or atoms of different elements. So we have chlorine atom had 7 electrons in the outer energy shell, and this one will be the ion that we are going to get, and I'll put here a negative. So you can see that here the electron that we have indicated in this particular chloride ion here is a cross. This cross shows that it is an electron that came from sodium. The other electrons were electrons that belong to chlorine. Now, in a much more simpler way, we can be able to draw this structure or this bond without actually including all the electron configuration or energy shells, because we realize that in this case, the outer energy shell is the most important one. These other ones are not actually involved in the bonding. In this case also, this energy shell here is not involved in the bonding. So we are only going to include their outer energy shells when we are doing the bonds. So in short way, I'll just do this and say that this is the sodium ion. I only indicate the outer energy shell. And for chloride ion as well, I'm also going to include or indicate the outer energy shell only, so that we said it is going to be dots for electrons of chlorine, and finally a cross. So in this case here, we can say therefore that this kind of representation is the same thing we have here. The difference is that for purposes of examination or answering questions in exam, we don't have to give all the energy shells that are not going to take part in the bonding. So we can simply ignore this part here. You can see I've simply ignored that, and I've ignored this one in sodium ion. So I've included only the outer energy shells, because that's the most critical part of this particular bond. So this is a bond that occurs in sodium chloride, and this is what we normally call sodium chloride if we write it that way. You realize that there's kind of a coincidence here. While sodium needs to lose 1, chlorine needs to gain 1. That is very good arrangement, so that we need 1 atom for each atom. Sodium 1, chloride ion also 1. You realize that now once this one is a positively charged ion, this is a negatively charged ion, and we know that a positively charged ion is called cation, and this one is anion. Anion is negatively charged, cation is positively charged. We know that for them to be positively charged, sodium had to lose electron for it to be stable. For this one to be an ion, it needs to gain 1 electron to be stable. But once they were stable, or once they are stable, then they form charges. These charges then attract each other, and that's where bonding now comes in. We know force of attraction between positive and negative charges. This force of attraction, we normally say it's electrostatic force of attraction. Electrostatic force of attraction. But as we are going to see that even in covalent bonds we have electrostatic force of attractions, in metallic bonds we also have electrostatic force of attraction. The difference actually is between what and what. In this case we are talking about ionic bonds being the electrostatic force of attraction between positive and negative charges. Between negative and positive charges. In this case the charges are ions. So we can say ionic bond is electrostatic force of attraction between positive ions and negative ions. And that's what I want us to understand today, that for bonds to occur, bonding only results because these atoms need to be stable. Stability means they either have to gain electrons or lose electrons. And when that happens, these particles or these atoms become charged. Charged atoms are actually called ions. Once they are charged, we have one which is negatively charged, one is positively charged. So the force holding them together is what we call the electrostatic force of attraction. But in this case, we have electrostatic force of attraction between positive and negative ions, and that is what ionic bonds are. We want to continue with our lesson. Talked about a much more simplified form of ionic bonding, but now we want to go to a much more practical ionic bond. We know that sometimes when atoms, elements react, for example, sodium is monoatomic substance and it's a solid, it's a metal. We know chlorine, for example, is a diatomic molecule and it's a gas. When this reaction occurs, we get sodium chloride, which is also a solid. If we balance this equation, we are going to have this particular kind of scenario. So I want us to be able to transform this kind of reaction into ionic bond so that we see what is actually going to take place in a practical sense. Because the previous lesson we talked about chlorine as being a monoatomic, which actually is not the case in real life situation. We know that this thing must exist as diatomic. So if I want to do the same, I know that these are monoatomic atoms, so I'm going to draw sodium atoms here. 1, 2, 8, 1 for this particular reaction. They are reacting with chlorine. Chlorine, as I have said before, it's a diatomic molecule, and this diatomic molecule it has a covalent bond inside there. So that one is going to be the two chlorine atoms overlapping. If they overlap, and like I said before, I can simply remove these inner energy shells, because as I know, I'm not going to use them in the reaction. So after I draw them like that, I can simply indicate that my molecule is going to be this way. This is 2, 6, 8. We know that. So we have the two atoms of sodium, this and this, reacting with a molecule of chlorine. That's exactly what we have this in particular equation. When I draw the arrow, so I'm going to have one atom. We have seen this before. We are going to have one chlorine atom going with this sodium atom, this one breaking out and going with this. It means that first of all, the two have to separate. When the two separate, we are going to see that this one we are going to have 1, 2, 3, 4, 5, 6, plus 1, 7 here. And this one 1, 2, 3, 4, 5, 6. So this one atom came from here, this one came from here. So they are going to separate, and each of them is going to have that particular atom of theirs. Again, in this particular case, we know that one electron will be transferred to the chlorine atom, and one electron here will go to the other one. So finally, the equation where the product we are going to have is a sodium ion, with 8 electrons in the outer energy shell. Sodium ion with 8 electrons in the outer energy shell. And we say this is how we indicate it. We draw the chloride ion because the compound has to be with both. And I said we don't need to show all the electrons or the energy shells. We just need to show the outer one that is taking part in the reaction with the bonding, and that is this particular one. Say these are dots, with one cross with a dot, a dot, a dot, a dot, and a dot here. So we have now one ionic bond, but we said that there are two. You can see here that there are two. Now in this particular case, you have two options. Either you can simply come and say this is 2 here to indicate that now this molecule or this ionic bond here, there are 2 of them, or you will actually be forced to draw 2 of them. Drawing 2 of them will actually be this way. You'll be forced to draw 2 of them, and this is what you are going to have. This is chloride ion. There. So we have this now what we are going to have. This is exactly what we have here. This kind of reaction, our body is small, we could have drawn it in a horizontal manner, but still you can understand that this is the sodium we have here, plus chlorine molecule that we have here. The product is actually this that we have here. You realize that this may not be a very practical case. We know that sodium and sodium can never follow each other in this manner particularly. So in a very normal scenario, we'll expect chloride ion to be here and sodium ion to be there, so that the ions interchange for that attraction to be there. So that while this sodium attracts this one, we need to have a sodium ion down here, and we need to have a chloride down here. That's where attraction will take place. Let me actually change that so that we see what I'm trying to show you. This is a dot, it's chlorine, change this to sodium, then everything changes to crosses. So we have crosses all over. This is plus, this minus. So when I draw these things actually this way, it makes more sense, because we said that it must be attraction between positive and negative ions, so that there will be attraction between this ion and this ion. Chloride also, this attraction here, there's another attraction here, there's another attraction here. That is how actually atoms are arranged in ionic bond. The first case which I drew, where sodium and sodium was following here, a student can actually ask that there could be repulsion, because if there's positive and positive and then negative and negative, we know that those charges will repel because they are not like charges. Viewers, quickly, I want to move to another example, which is magnesium. Magnesium reacting with chlorine. Or let me say magnesium react with oxygen first. If magnesium is actually reacting with oxygen, we know that we have Mg plus O, and oxygen is also diatomic, so we are going to have MgO. We balance by having there 2. This is solid, this is a gas, this is a solid there. So we have magnesium react with oxygen, but as we have seen before, oxygen here is diatomic, so we must have a covalent bonds of sodium. In this case, I want just to go to the outer energy shells only. So if I have magnesium, I know magnesium, the outer energy shell has 2 electrons. So if it has 2 electrons, and then I will have 2 of them. So magnesium here having 2 electrons in the outermost energy shell. But this one is with the assumption that I know there are other energy shells here. For example, the first which has 2 electrons, the second which has 8 electrons, and then the third here has 2 electrons. I know these 2 electrons will be lost. Once the 2 electrons are lost, then the next energy shell that is going to be having 8 electrons as we go inwards is going to be the one with 8. That is going to be seen once we draw the compound here. Plus here I know oxygen is diatomic. If it is diatomic, and also is covalently bonded side. So this is oxygen atom, 12 we have there. Now these atoms, the way we have drawn here, we are showing exactly what will take place in a reaction. But before this actually oxygen atom reacts with this magnesium and the other one reacts with this magnesium, they must first of all be separated. The separation means that we are going to have oxygen with 6 electrons outer energy shell, and this one also separately with 6 outer energy shell. 6 means that the oxygen atom requires 2 electrons, magnesium can lose 2. That's a very good combination. Lose 2, gain 2. So we are going to have here, the compound will be having magnesium oxide losing 2 electrons, and I said that we don't have to draw the other inner energy shells. I said here we were drawing outer energy shells, which were 2. These 2 electrons are the ones that are going to the oxygen atoms on the other side. So if we remove this outer energy shell, the next outer energy shell will be having 8 electrons. So we'll have those 8 electrons here. 8 electrons. But this one now becomes magnesium ion. Magnesium ion with the 2 positive. And we know that on the other side, oxygen atom will gain 2 electrons from magnesium to form an oxide ion, and that will be O here. If I draw that, the outer energy shell, we know that there are 2 electrons from magnesium with the 6 dots that were there before. So that is what we have, and this will be 2 minus. If I have another one, because as we have seen there are 2 of such bonds, we have just drawn one. And like I said before, for attraction to take place, it means that in this case now, I cannot put magnesium here because then there will be repulsion here. Magnesium must be on the other side. Now we have oxide ion here. That's 2 minus. So we'll have O, this one coming here, dot, 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 dot. Let me say we have 2 crosses, dots there. And here, therefore, I bring in magnesium ion, Mg. I know that now the outer energy shell here will be having only crosses, and there are 8 of them because we have lost 2. This one will now be what we call the reaction that we have here. This is what we have here actually. I said that alternatively, if you don't have to draw this 2 because it may be tiring, you may actually remove this one, but you have to indicate 2 here. If you put 2 here, then it means that this down the row below, the bond below will not be there, because already we have said times 2, exactly what is happening there. So this is a more practical case of magnesium reacting with oxygen. Now quickly I want to show you something, and now I don't want to give you equations, I want just us to understand something. What about if we have been talking about a case where the metal needs to lose 1 and the non-metal needs to gain 1, in the case of sodium, of chlorine and sodium. In this case, we have looked at a case where magnesium needs to lose 2 and chlorine needs to gain 2. But now I want to talk about a case where, for example, we have magnesium and chlorine. Magnesium atom and chlorine. Magnesium is having electron limit of 282, while chlorine is 287. What we can see from here is that magnesium needs to lose 2 electrons to chlorine, but chlorine can only gain 1 electron, at a time. So if chlorine can only gain 1, and this one can lose 2, we know that by this chlorine atom gaining 1, yes, it is stable, but magnesium is not stable because still there's 1 electron. It has only lost 1. So in that case here, we actually need 2 chlorine atoms so that each chlorine atom will gain 1 electron from magnesium. And so in this particular case, we are going to have 1 magnesium atom with 2 chlorine atoms. And that one appears this way. So we'll have Mg. I'm going to draw the ionic bond directly without having to, and I know that the outer energy shell now will be having 2 electrons. 8 electrons in the outer energy shell, and there must be a bracket because it is ion, and this is 2 plus. But there are going to be 2 chlorine atoms. I want to draw one on the other side, one to be on this other side, and another one to be on this other side, so that I will have Cl here. The outer energy shell, there is 1 cross from magnesium and 7 dots. Those are the 7 dots like I've drawn. When I come here, I will draw the same chlorine atom here with 1 cross from magnesium with 7 dots, the original number of electrons that were there before. This is negatively charged, this is negatively charged. So you realize that we have a case where we have Mg plus Cl2 to give us MgCl2. This is what we have here. So if we are to react one magnesium atom with two chlorine molecule which contains two atoms, we are going to have magnesium chloride. Magnesium chloride where we have one magnesium atom with two chlorine atoms or chloride ions, and that's exactly what we have here. So we have this and we have this too. That is a case where we have magnesium with losing 2 electrons, chlorine gaining 1. You can have an opposite side where we have magnesium gaining 2 but sodium losing 1. In that case, it's going to do the same thing where you have one oxygen atom with the 2 sodium atoms. In that case, we can have something like this. If I have a case where we have a sodium which is 281 with maybe oxygen which is 26. So in this case here, oxygen needs to gain 2 electrons, but sodium atom can only lose 1. In this particular case here, we have a case where we are going to talk about 2 sodium atoms. 2 sodium atoms coming in to give out 2 electrons that will be gained by oxide ion. So if I draw oxygen, I will draw oxygen because oxygen, I'll draw it at the center, is the one that is taking 2. That is oxygen. Then I'll draw a sodium here. Then another sodium here. So all of them are in brackets. This one also in bracket. This also is in bracket. So I know that sodium, if it loses 1, it will be having 8. The outer energy shell will now be having electrons. That is positive. This is also the same. 8 crosses because we have lost the one with 1 electron, and that is positive. Then we have oxygen here, 1. Let me use dots. Dots for oxygen. Then have that. Then have that. In this case, I know oxygen has 6 electrons in the outer energy shell. So the dots are the fun for oxygen. 1, 2, 3, 4, 5, 6. This cross here is for 1 sodium that donated it, and the other one lost 1 electron that came here. So finally, oxygen atom is now stable with 8 electrons in the outer energy shell, and the sodium is also stable here. This one is also stable. You realize that if you are writing the equation for sodium reacting with oxygen, let's try to balance it. We are going to have sodium oxide. We have to balance there by 2. This will be 4. Yes, so if that is the case, that's what we have when we are writing equation between the reaction between sodium and oxygen. Then it means that this one here, if you're drawing these compounds here, you can either put here 2 to show that these compounds, this bond is 2 of them. You can see here, this is 1, but there are 2 of them. Or you can draw this row and draw a similar one down there so that the total number of sodium atoms or ions are 4. And the one for oxygen are 2. This one plus the one that will come there below. But for sometimes to make your work shorter, you can just multiply what you have done by 2. That will give you a better clue of what to do when we are drawing ionic bonds. We are able to look at how to draw the ionic bonds using a dot cross diagram. Today we want to move on to what we call giant ionic structures. I want to invite you to understand that a bond which carries 2 ions, for example, sodium chloride, sodium ion with chloride ions, this is something that we cannot see with our naked eyes. It's too small. For us to have a salt, for example, a table salt, which is mainly made up of sodium chloride, we must have many of these bonds put together. We must have very many, millions and millions of this kind of sodium chloride ions, very many of them put together to form something very huge. And that very huge thing, we are going to call it giant ionic structures. So in a structure is the real thing that we see. A bond is something that is actually giving rise to that particular structure, but we cannot see it. So when we talk about a salt at home, the table salt that we see at home, we can use actually put in soup or in food. That is something we should know. Actually, we can call it a structure. That structure has millions and millions of sodium chloride bonds. that we have seen before. So before you here, I've actually drawn something, 2 cubes. The first part of the cube, forgive my drawing is not to scale, but it can be used to demonstrate what I want to explain. The first cube is here, then there's a second cube. It's very clear that sodium chloride is cubic, is crystalline, it's a cubic crystal. It's a cubic crystal. It means that the crystals of sodium chloride are arranged in cubes. 1 cube plus another cube plus another cube. That is why every time you break a piece of salt, you should still have a regular shaped crystal. So in this case here, if I have a structure this way, and this structure we're going to call it a lattice. What is a lattice? A lattice is defined as the regular arrangement of positive and negative ions in a structure. So in this case, why do we say regular? You can see that actually we are forming something with a regular shape, a cube. A cube is a regular shape. We know that a cube has the length, height are the same. So we normally say L, L, L. So this is a regular shape. That's why we say lattice, ionic lattice in this case is a regular arrangement of positive and negative ions within ionic structure. Now, if I have these circles I've drawn here are the ions. They are going to represent our ions, and in this case we are talking about sodium chloride. So meaning we have sodium ions and we have chloride ions. If I start by saying that this one is a sodium ion, for example, the first cycle, then we said that for attraction to occur, ionic bond is the electrostatic force of attraction between positive and negative ions. So if I have sodium ion here, for attraction to occur, the next ion must be a negative one, which is a chloride one. And the next one after that must be positive one. So I'll have sodium ion here. The next one, if I go there, must be a negative one. If I go there, it will be a positive one. If I come here, a negative one. If I go there, a positive one. If I come down here, negative one. What about if I follow this line here? It will be sodium ion. And you can see this sodium ion and this is negative. So there's attraction here, there's attraction there, there's attraction here, there's attraction here, there's attraction here. Here, if I move from here to here, this one should be plus, chloride ion. And then from chloride ion, if I go there, I should have chloride ion. So you can see that actually when you are drawing a giant ionic structure, giant ionic lattice, we need to be able to alternate. There's one missing here still. So if we follow here to here, we are going to have this one as a negative or a negative ion, that is chloride ion. So we must be able to alternate. Sometimes in examination, they may draw big cycles and small cycles until the small cycle is the chloride, the sodium ion, and the big cycle is the chloride. You need just to know how to work with that. They will give you a key. Sometimes they may tell you that the positive, they just put this one positive and negative, so that they tell you the positive sign represents the cation and the negative sign represents the anion. Whichever way it comes, learner, you just need to know how to adapt to the question and be able to understand what you need to do. In this case, I'm now trying to change. If we used a different way of asking the question, you just need to know how to deal with it. So that is it. I've changed everything now. In this case now we can assume that a cycle with a positive sign in it represents the sodium ion, and the cycle with a negative sign in it represents the chloride ion. That is what you need to know. So this is what we call giant ionic structure. And I've said in the stable salt that you have at home, given that our example is sodium chloride, you have many, millions and millions of this kind of cubes put together to make the salt that you can actually see. And today I believe we can be able, if you have a box or a cube drawn like this for you in examination, one part is filled for you, the other ones are blank, then you can be able to use the concept you have followed, that you have to alternate. from positive to negative, negative to positive, to be able to fill the whole document. That actually will award you some marks. So learn that is about the giant ionic structure, giant ionic lattice, and today we have to be able to know how to define giant ionic lattice. And I said ionic lattice is the regular arrangement of positive and negative ions in ionic structure. And when we are doing this kind of structure, you need to be able to alternate the cations and the anions, because in that case is only the way you are going to get attraction between them. If you follow positive with another positive, meaning a cation plus another cation, there will be repulsion instead of attraction. I want to also to invite you to understand that in this case you can see one ion here, another ion here. This is not very practical. We have drawn a cube to be able to illustrate what is seen. But in a real case, this ion and these ions are actually close to each other. They are touching each other here. You should actually find something like this. But you know, it's very hard for you to draw things like this, to make a cube like this, very complicated. So in a real life situation, we don't have this distance here. But in this case, this distance, we are showing it to be able to illustrate to you how this cube actually appears. The line between these two ions actually becomes the ionic bond. So we can see that in ionic structure, we have a network of ionic bonds. All of these ones are ionic bonds holding everything from one corner to the other. We cannot say that we only have one ionic bond between two ions only. No. This one is between this, but again, this ionic, an ion here is attracted to another cation on the other side, and also below it down here, and also on the other side. So you can see actually that there's a series of interaction between these ions in this particular structure. So I think I've explained, and if you have any questions, please don't hesitate to contact us. Thank you very much for that lesson, and please stay safe.